Yeah, comes on everyone. Let's start off. Sure, let's start off. So last thing we have done with the buy and force thing. This is a PYQ. JEE 2006, the year I wrote the exam. Let's get this. So here I drew one more diagram here. So we have a wooden cylinder of diameter 2R. That is this guy. So diameter is 4R. So radius is 2R. Right? It is placed on top of a hole of diameter 2R. So this thing white here, this is a hole of radius 2R. Making sense? H1 is the height of the liquid above the container. So this is H1, right? And H2 is the second part, meaning I'll just draw the diagram for that also. The picture is not that clear. So the second part is this. The liquid is filled till here. This part is H2. Go through the question once. Get the first one. I'll give 2 minutes for the first one, then I'll give another 2 minutes for the second one. So question is not really that tough or something, but the main idea is this. Can I use bind force here? That's it. That is the main catch there. If the lower surface is not covered in liquid, you can't use bind force. That is the only catch about the question. Give it a try. So this came in 2006 JE. My friends used bind force and messed up. I used pressure. I got the answer. Anyone didn't get the question, please ask me. If the diagram looks confusing, do ask me. I'll show you. But this is how the question was actually framed. That is because you didn't read the, you're not revising the notes. Arya, should revise the notes. What did you write here? This was the page that we discussed. You can't use bind force if the lower part is not completely covered with liquid. Clear? Because that bind force is defined as F upper minus F lower, lower minus upper. The lower is not completely liquid. Did everyone got the question? So when you keep on decreasing the liquid level at a particular height h1, the block is lifting off. Find h1. Then the second question is, if you continue decreasing, it will try to lift off, but someone is preventing by applying a force. But once the water will becomes h2, you need not apply any force. So find h2. So there are two parts there. Get the first one. You just need to draw an FBD. You have to consider. Why won't you consider? Yeah, let me show you the free body diagram. So what are the forces? So from the bottom in this part, the force will be P naught into pi r square. From the top, the pressure here, if you see the liquid is height up to h1, which is P naught plus rho g h1 into area will be 4 pi r square. Agreed? And your own weight mg. And remember, this guy is standing on a platform here, so there is also a normal reaction n. And also there is a force on this part here, side mein. Let's call it F, where F will be the pressure at this bottom. How much is this height? This is H P naught plus rho g H plus H1. And what will be that area there? 3 pi r square, na? Pi 2r whole square minus pi r square. I'll write that if you want. So the lower part has two different kind of pressures. One is the atmosphere pressure and one is the liquid ka pressure. Atmosphere is acting for an area of pi r square. The liquid is acting for 3 pi r square. There are 5 forces on this, everyone. Have a look at this. Arya, clear this? The reason why we can't use buoyant force is because of this. Because the definition is what? The force due to the liquid on the lower surface minus force due to the liquid on the upper surface. The difference is buoyant force. But at the bottom, it is not completely liquid anymore. Ah, Vihan, clear with this? And you said it is in equilibrium. And look at this word here. The block just starts moving up, meaning it loses contact. So if it loses contact, then the normal reaction is 0. So just balance the forces. Upward forces will be F plus P naught by R square plus N will be balancing mg plus P naught plus rho g h1 4 pi R square. Just have a look at this. And then N is 0. F will be P naught plus rho g h plus h1 3 pi R square plus P naught pi R square. What is M? The density of the block is rho by 3. Rho by 3 pi 2r whole square. Height is h plus P naught 4 pi R square plus rho g h1 4 pi R square. From here you can see this term P naught, this term will cancel off. You will be left out with rho g h also will cancel. You'll be h3 into h plus h1. This is 1 by 4 by 3 h plus 4h1. This guy will be 3h minus 4h by 3 is h1. So h1 will be 5h by 3. Yeah, that's your C answer. Do have a look at the steps. Like I said, as such, there is nothing in the question. The only thing you need to realize, boss, you can't use buoyant force. Any doubts on this? Have a look at this. Next thing, look at the second question. Now give it a try. Now you got the FBD how it looks. Now give it a try. I'll give you a minute for the second one. What did we take FS? FS, this guy, na? If you look at the bottom, you should take the pressure into this area. No? Pressure will be how much? Rho g h plus h1, total depth. Right. Try others. I'll give you another 30, 40 seconds. Parth, question is clear? Give it a try, na? Then give it a try. Don't wait for someone to answer. You should all try on your own. Who is going to come and help you guys in the exam? Try it. It's okay if you get a wrong answer, but try. Give it a try. And when I show you, you can compare and see whether you got the steps right. Let's see. Remember, this time liquid is only till here. This height is h2. So from the top, we have P naught into 4 pi r square, your own weight mg, P naught into pi r square. The force F will act on the 3 pi r square area. F will be P naught plus rho g h2 into 3 pi r square. Since you're sitting on that platform here, there is also normal reaction. So technically, the 5 forces are there. But again, same thing. He said it is about to lift off, so P naught pi r square plus F plus N S mg plus P naught 4 pi r square. So this guy is 0. K naught pi r square, P naught 3 pi r square, rho g h2 3 pi r square. Mg will be rho by 3 pi 2r whole square hg plus P naught 4 pi r square. So this guy, and this guy is gone. Rho g r square is gone. This will be 3h2. This will be 4h by 3. h2 is equal to 4h by 9. Easy? Clear with this? Any doubts on this? Clear, everyone? Jainil, Vihan, Soham, Arya, Devansh, Nikhil, Jainil, Ishana. Clear, na? Purvaja, Parth. Clear. Next one. Similar one. Let's say we have a hole here. We have a solid cone here. Blocking the hole. Cone ka this radius is 2r. This hole ka radius is r. This is r. This is r. So cone ka height is 2r. Radius is also 2r. Let's say cone ka density is rho by 3. Now what you did, you started pouring the liquid. Let this height be h. Liquid ka density is, let's say, rho. Same thing here. Find h. Well, let's do one thing. So someone is also applying a force F to keep the cone at rest. A force F external is applied to keep the cone from coming out. इसमें problem आएगा because then the normal reaction will come. You won't be able to calculate that. We'll keep it like this. Find h when the cone just lifts off. Let's say I hope I gave that data right. Yeah, let's see. The process is more important. Data I can always adjust. Is the question clear? It kind of looks like the similar to previous one, right? But I changed the shape. In this, there is one thing I wanted to show you. Try. Problem is fine. If you got that one thing, how would you take the main problem will be this guy. You try for a minute, then I'll show you. You should not reveal everything. हाँ वो कैसे कैलकुलेट करेंगे वही प्रॉब्लम था अंश Did you guys realize who is creating issues here? When you draw the FBD, there is one force which will create issues for you. Side walls. Cylinder में ना the side walls cancel out. But here, if you look at the side walls का force, this thing comes like this ना. उसका vertical component आएगा. How will you take that? Think. I'll give you 2 minutes. It's a worthy question. Let's see. Integration will not be possible there. That will be too complex. Listen to this. This is the main idea there. For example, let's not consider the whole cone, just consider this part of the cone. Okay, and let's say if this guy is in the fluid. Now, if you look at the forces acting on this, so we have a force from the top, we have force from the side, and we have force from here, and we have force from the bottom. So this is the force from the up. This is the force due to the side walls. I'll just write it as F side. And this is the force due to the bottom. So force due to the bottom plus force due to the side walls minus force due to the upper part. This entire resultant is nothing but the buoyant force. Do you agree? Do you guys agree with this statement? Isn't that how we define buoyant forces? Now, F bottom, I know how to calculate. How much is that? So here, F bottom, if you see, this guy ka total depth was H plus R. So F bottom will be P naught plus rho G H plus R into that area is pi R square plus F side walls minus up also. I can actually calculate up also, but okay. Buoyant force will be what? Density of the liquid, volume of that part. How much is the volume of that part? So from a full cone, we have done this before. From a full cone, we need to subtract this small cone. Then you're going to get this piece. This will be 2R. This is 2R. This is R, and this is R. This is 1 by 3 pi 2R square 2R minus 1 by 3 pi R cube. This guy will be 7 by 3 pi R cube. So this will be 7 by 3 pi R cube G. So from here we got the F side walls minus the F upper is rho into 7 by 3 pi R cube G minus the P naught plus rho G H plus R into pi R square. Is this clear, everyone? So I got the F up and F side walls cut together component. Have a look at this thing. So actually F up also I know, right? Which is P naught plus rho G H into 4 pi R square. I could have calculated F side walls also. Now, when you draw the FBD now, look at the forces. Your own weight mg. This is F up. This is your F side walls. And the atmosphere here is pushing with P naught. Now remember, P naught is constant. So I can use projected area, which is P naught into pi R square. That's it. Any other force that I missed? You're about to lose contact, the normal reaction is 0. Now, when you balance the forces, we get F side plus P naught pi R square will be equal to mg minus F up. So this is F side minus F up plus P naught pi R square is equal to mg. Now, what is F side minus F up for this guy? Rho into 7 by 3 pi R square G minus P naught plus rho G H plus R pi R square plus P naught pi R square is equal to mg. mg will be rho by 3. You should take the full cone. So 1 by 3 pi 2r whole square 2r into g. Any doubts still here? Please ask me. So the main idea in the question was this part, right? How do you get that f side walls without any integration? And this comes from that argument buoyant force is nothing but the difference in force due to the lower surfaces and upper surfaces, isn't it? I know how to calculate for the upper surface, I know how to calculate for the lower surface. So that means the side forces will be nothing but total buoyant force minus these two. Is this base clear, everyone?
Sir.
Mehan.
Sir, basically what we are doing here is we're taking a different scenario where we're just letting it flow in liquid, and then we calculated the difference.
That side force, yeah. Because see, the thing doesn't care whether you're sitting on this hole or you're just standing in a liquid, right? As long as the depth is same, why will the liquid care what is there below this point, isn't it?
Yes, sir.
Make sense? I mean, tell me one thing. Why will this force change? Because there is no liquid below this. Make sense?
So, sir, that's why we didn't take the force at the bottom for the second FPT because it's not exposed to the water.
Because this thing is case mein na, there is no water only there. So here ये F bottom लेना ही नहीं चाहिए था.
But
In
with
place
the
of F bottom, you are
difference
getting P naught by R square.
but with a different scenario, वो same होगा.
Yeah. Because the argument is this thing, right? Suppose if there had been a liquid, F bottom would have been this. You're getting it. So the remaining forces would be, I can calculate the remaining forces, right? So my argument is these remaining forces don't care whether this part is exposed to liquid or not exposed to liquid. Is that sentence making sense, everyone? Why will force on one surface change because of something else? Second step mein, this is Fs minus F up. ये plus है ना, my mistake. F up is down, na? Clear with this? I think you're done now. You just need to solve. So this P naught pi r square ka term will cancel out. Yeah, P naught pi r square ka term will cancel out. Rho 7 by 3 pi r square g. This will be P naught into, why did I cancel this? I will cancel this guy. P naught into pi r square ka term is cancelled. Then you are stuck with rho g h plus r into pi r square. This guy will be 8 by 9 rho pi r cube g. So rho will cancel. Rho pi r square g will cancel. So we are left with 7 by 3. Yeah, I missed something there. ये cube है. This was cube. So this will be 7r by 3 minus rho is cancelled, pi r square is cancelled. So you are stuck with h plus r. This guy will be 8r by 9. Perfect. How much is this? 7r by 3 minus r. 4r by 3 minus h is equal to 8r by 9. Therefore, h is equal to 4r by 3 minus 8r by 9. Multiply 3, that is 4 3 is 12. 12 minus 8 is 4, so 4r by 9. Yeah. Is this clear, everyone? This is how an advanced paragraph will look like. Ansh, clear now? Yeah. Any doubts on this? Please ask me.
Sir.
Yeah.
So we could use this technique for any type of
Anything actually. Yeah, it would work for anything. But वो क्या है ना, F bottom you should be able to calculate. For example, if you give me something like this, but F bottom try to make it flat.
Yes, sir.
But if you give me F bottom also like this, then I don't know what to do. Getting it? That F bottom has to be flat. As long as the F bottom is flat, you'll be able to do this. Okay? But got the technique, right? That is the thing. Great. Next one. Stability of ships. So what happens if you put a ship in a water? So when they design ships, right? Let's say if this is your center of mass, where mg is acting, this is your center of buoyancy, your fp is acting. So this is one way to design a ship. You make the center of mass at the top and buoyant forces below. Or you could do the same thing. Center of mass is below, the buoyant force is above. You tell me, how should we construct the ship? Which one is right? See, you can change the center of mass by making the ship heavier at the bottom. Or you can make the ship heavier by putting more floors on the top. So center of mass can be shifted up or down by adjusting the mass. So if you're building a ship, which is the proper design? Now see what happens. So let's say there is a big wave comes and hits the ship. So this ship tilts a bit. So your mg will be somewhere here. Your buoyant force will be somewhere here. Now you tell me, how is the torque? The system is trying to rotate this way, right? So the ship torque also will be this way. Now you see, the ship tilted towards the right and the torque is also towards the right. What will happen? Will the ship stop? Will it come back? It will just keep going, right? This is an unstable equilibrium. The ship will completely turn, getting it, and it will become like reverse. The hull will come up and the ship will go down. But in this case, if the ship tilts towards the right, mg is here. The rotor was it. Mg is here. The buoyant force is here. Now what will happen to the torque? The torque will be this way, right? Now you tell me, what kind of equilibrium is this? This is a stable equilibrium, right? If I push you to the right, you'll rotate to the left. If I push to the left, you'll rotate to the right. This is a stable equilibrium. So how you want to design the ship? B case, right? So when they design the ships, they make sure the base is heavier. So that is the reason they keep the engine room, the cargo, all the used water, all the fresh water, everything that can be heavy, they keep it at the bottom. They try to make the ship ka base as heavy as possible. And that is the reason if you see oil tankers, right, these are like damn stable. Like put them in a tsunami, also nothing happens. Whereas the most unstable ships are actually cruise ships. Because no one wants to stay in the under the deck, right? So everyone wants higher floors and better views. So you have to build more floors on the deck. So center mass actually shifts towards upper side. And that's the reason what they do in a cruise ship, they build all the casinos, the restaurants, right? All that thing, they try to keep it inside the ship at the bottom. They try to make the base as heavy as possible. So while building the ships, this is what you do. So for stability, center of mass has to be below center of buoyancy force. So some few years back, right, there was a ship which was carrying potatoes, right? And the ship got fire. The potato got in the room, right? So how they're carrying, no, they're putting all the potatoes in trucks and they kept the trucks inside the ship. So when the ship reaches the port, the trucks can just get down and directly go to the place where they need to go. Normally, that's how you transport. So one of the trucks got fire, and the fire started spreading. This was on somewhere in the middle floor, meaning the ship was something like this, and somewhere on this floor, the fire got caught. So these people, the sailors went inside with this firefighting machines and all. The water sprinklers were there. They're spraying water. These people are spraying water. Now, what happened after spraying water? That water has to go through the exit, right? Somewhere. But all those exits got blocked by potatoes. The potatoes are jamming the hole. And then what happened? This entire floor started getting filled with water. The center of mass started shifting. The ship started tilting. They stopped the sprinklers. They stopped spraying the water. The fire started increasing. So if you don't spray the water, ship will burn. If you spray the water, ship will overturn. So one of the firefighter, he just went there and started clearing the potatoes. It was a mess. They couldn't do anything. Finally, somehow they controlled the fire for like few hours, and they took it to the nearest port. And they anchored the ship, and then they brought the fire engines and all, and they tried to stop it. Finally, ship was saved. So that is how a potato can sink a ship. So they were in a situation like you spray water, ship will turn. If you don't spray water, ship will burn. So what to do? Potato kills. Yeah. Clear? That's a bit about fluid statica part. The next part is fluid dynamics. We have 8 people who got 99 percentile in physics. Now they're writing board exams. Their advanced preparation will start again, I think, in 3 weeks. And we have a lot of 98 percentiles also. We study fluids in motion. So we'll be having a PTM also soon. I think in 1 or 2 weeks, I'll be taking a PTM for you guys. So there are a few people who are not writing the exam. I need to talk about that. And the challenges you're going to face now, in case you forgot, you're in 12th now. Right? Nothing's are going to get pretty weird. I won't say tough to hai, things will get more messy. We'll have a small discussion on that. So this is called control volume. That's a very technical way of saying this is a region where you study the liquid. So you don't actually study molecule by molecule. What you study is a small region of fluid. So what do we study here exactly? Remember, in fluid statics, we are more interested in the density, the pressure, and all this stuff. So in fluids, we call them flow or field variables. Again, a technical way of saying the things which you study. The first variable is pressure, or obviously. So we like to see how will the pressure change when the liquid flows. Second thing, velocity of the flow. Third, the density. Fourth thing, the acceleration of the particles. So if I know these 4 things about the liquid, I know everything about the liquid. I can figure out all the data there. So when you say this particle, exactly what do you mean by that? So are you talking about a molecule? No. So when we say particle here, what it means is you take a small sample, a collection of molecules. So we are taking the average speed of all these molecules. And that's what we call as the speed of the velocity particles, the liquid particles. So let's say you take a small space of 0.9 millimeter cube, and we say it's uniform everywhere. You're considering average speed of all these molecules. That's what is called as collection of molecules. For example, see, when your blood is flowing, your red blood cells are going with a different speed, white blood cells are going with different speed, plasma is going with different speed, platelets are going with different speed. So nothing is going with something same. So when we say the speed of the blood flow is this, what you're talking is actually the average flow. So when you say the speed of the liquid is V, it doesn't mean the water molecule is going with so and so speed. So it's an average. So whereas the individual molecules can have different speed. Clear with this, everyone? Next one. Great. Now, studying fluids is actually very difficult. If you remember last time I was telling you, there is something called Stokes-Navier theorem. There are 5 equations, right? Millennial equation, they call it. One is solved so far. There are still 4. So in that, one of them is a Stokes-Navier thing, which actually you can study theoretically. When a liquid flows, you can study everything about it. So we have the theory about it, but we don't have the max to solve that equation. So if you solve that, you get $1 million prize. That's like max ka Nobel prize, you can say. And things actually advance a lot. Those solving those mathematical equations helps a lot in science. So it's very difficult to study fluids. So tomorrow, if you're designing a ship also, right, you don't have a theoretical way of saying how will the ship behave in a particular liquid. So what they do, they make a model of the ship. In IIT Madras, right, we have a big wave pool. It is almost 3 times the size of a swimming pool. It is the Asia's largest wave pool. So in that wave pool, you can create different waves of heights up to 2 meters. So in that, they have a lot of things that. So what they do, right? You can have a ship there. So they keep the ship stationary. They move the waves. So it gives you a feeling the ship is traveling through the waves. Or let's say you're designing bridge ka pillars, right? And when the waves are continuously hitting, for example, right now they're making the coastal road, or if you take that, what is that thing, right? The bridge thing. Forgot the name. See, वो है ना Bandra में that big one, Sea Link. So those pillars are in the sea, right? So continuously they're being battered by the ocean ka waves. So if you don't design them properly, there is a chance, they'll get eroded and someday the pillars will lose their strength. So how do you design them? So they make a miniature version of it, 1:100 scale. They put it there and they test for different wave speeds and different situations. So there is no way theoretically we can study them that easily. So that is how they do that. So if you're in naval architecture, you'll be going there. Pool is pretty dirty. You should not try to swim, right? So that is there. It is still not temperature control though. But if you go to some other US and all, right, they have pools which can be frozen to ice. Depth, I think, is almost 4 meters, I guess. 3 to 4 meters ka depth. 3 meters depth. So it's a pretty decent one. So streamline. So what is a streamline? So we study a very special case of it. So a streamline is a curve which is tangent to the velocity of the liquid particles at that instant. Now, what this means actually, technically, what it simply means is a streamline is the path of the particles. So the path of the particle is called a streamline. So the velocity vector is tangential to the streamline. So if you draw a streamline, remember in heat transfer, we did this thing steady state. So any particle that comes to point A will have velocity VA. Any point that comes to point B will have velocity VB. So the path followed by the particle is called a streamline. So here velocity is constant with position but can change with time. So on a streamline, whenever you come to a certain point, the velocity is fixed with position. So all particles that reach point A have velocity VA. Sorry. And becomes VB at B. So velocity of the particles is constant with position but can change with time. This is just like that steady flow which I taught you in heat transfer. So a collection of streamlines is called a streamline flow. I'll show you how it looks. So if you take multiple of the streamlines, it's called a streamline flow. It's called a streamline, comma, steady flow slash laminar flow. So there are multiple names for this. This is what we study. We study only streamline flow, which is actually easy to study. Theoretically, it's manageable. Let's see a few more points about the streamline. Let's see. So two streamlines never intersect. Why? Because look at the definition. It is the path of the particles. So if you have two streamlines, meaning you're saying the particle is going in both the lines, that's not possible. So streamlines never intersect. So another way to argue is, at the point of intersection, there are two tangents. That means the particle will have two different velocities. A particle cannot have two velocities at the same instant. Therefore, two velocity vectors. So you can't go like along VA and VB at the same time. Second thing, higher the density of streamlines, faster the liquid flows. Meaning, now if you see, number of streamlines are 5 only. But if you look at this position here, and this position here, more streamlines are meeting at A. So here, if you see VB is greater than VA. Think of like this. Let's say in your classroom, so this is the class, and let's say this is the door. All are sitting here. After the class gets over, and when all are leaving, how do they leave? If you see, everyone is trying to leave through the door like this, right? So like each person is like a streamline. Now you tell me, where do people go faster? Near the door or away from the door? As you get closer to the door, what will happen? Everyone will start pushing, right? Arey, move fast now. You can't block the door near the door. So as they get closer and closer to the door, they start flowing faster and faster. So the streamlines are getting, they don't mix, but they're getting closer. You're getting it? So more streamlines are flowing in the lesser area, means the liquid is flowing faster. Clear? Next thing. So, so how does the streamline look like? So a streamline flow, right? So suppose the liquid is flowing in a streamline. And let's say you drop some ink here. You know what you will notice? The only this streamline will become red colored. The ink won't spread. Why? Think about it. What is the definition of streamline? The path of the particles. So whatever ink you're dropping on the streamline, they will just keep following the same path. So if you actually think about a streamline flow, right, it is like your traffic flowing on a Eastern Expressway or a Western Expressway. Meaning, assuming everyone is following, a proper lane, or even the traffic near the toll naka. You'll observe, let's say near the toll naka, right? Let's say this is one, this is one, this is one, this is one. So all the cars that are standing here, if something gets blocked here, this lane will get blocked, but the remaining lanes are just going as usual, isn't it? So if you take an orderly traffic on a nice highway and people are following the rules, if you see it is actually proper streamline. The car which is in one lane will keep going on the same lane until unless it needs to make a turn or something. So this is how you can say simply streamline flow. If you put ink on one streamline, it will not spread. Whereas the other one, so opposite of streamline is your turbulent flow. So it's called as turbulent flow or non-steady flow. These things we don't study. Here, first of all, there is no concept of streamlines. The liquid is messed up. It is flowing however it wants. So here, if you try to put some ink, you will notice after some time, right, the ink spreads everywhere. Because there is no specific path of the particle, the ink will go to every possible place. This is like your, the road near the station, or this near the cow gully, or best thing vegetable market. The autogay enters from one lane, right? And we have not sure like how this guy is going to go. This guy will come like this, take a turn like this, and will go like this. They will do any shit. So that is the best way to explain a turbulent flow. The traffic in a vegetable market. People are just coming from anywhere. You can't predict where that guy is actually trying to go. It looks like he's taking a left turn, but then he suddenly takes a U-turn and goes off somewhere. Clear with that. So that's your turbulent flow. So how do we decide whether the flow is streamline or turbulent? People tried studying it theoretically, but they couldn't figure out. So there's a guy called Reynolds. He came up with experimentally came up with some data. Because see, companies, right, they don't care about what is the mathematical equation. They just want to know, boss, when will the flow become turbulent? When will the flow become steady? And you want to see this thing, right? You can see this, you see this every day. When you open the water tap, the starting part of the water, if you observe, it is pretty crystal clear. Observe? Then after some time, the water becomes hazy. So whenever you open the water tap, the starting part of the water is actually going in a streamline. The remaining part is actually becoming a turbulent flow. So this guy came up with experimentally, it's called Reynolds number R, which is rho V D by eta. This is removed from the mains portion, but it is there for bits and other exams. So here V is the velocity, rho is the density, and D is the diameter. Eta is coefficient of viscosity. So what Reynolds came up with is, if the Reynolds number is less than 2000, the flow is streamlined. If the Reynolds number is between 3000 to 2000, it is actually transitioning. So it can be anything. It can be streamlined or can be turbulent, we can't say. If Reynolds number is greater than 3000, the flow becomes turbulent. Now, this is important for companies. For example, imagine you're running a pharmaceutical company, right? So if you're running a pharmaceutical company, right, and let's say you're trying to make eye drops, and in the eye drops, you have to mix 4 different ingredients. Now you tell me, when these 4 different ingredients are going through a pipe and they're getting into a bottle or something, you want the flow to be turbulent or streamlined? To make your eye drop ka solution, I have to use 4 different ingredients. So when I make them flow through the pipe, should the flow be turbulent or steady flow? You need to ask yourself, do you want the liquid to mix properly or don't want to mix properly? You want to mix properly, right? You want the molecules to be uniformly distributed. So you need to have a turbulent flow. If you make them go in a streamlined flow, then the bottle, then each layer will have different liquids. The liquids won't get mixed up properly. Is that making sense? That is the reason we are. So if everything is getting mixed up and there's no proper flow, you're getting it. The light will, in a streamlined flow, the light is always refracting in a particular order. When you're continuously breaking the surfaces, the light gets refracted at different ways. It starts looking hazy. So now this is a theoretical question. So to get a streamlined flow, this is a question they asked. For a streamlined flow, which of the following is true? High density, high viscosity, low density, low viscosity, high density, low viscosity, low density, high viscosity. It's a 4 options. For a liquid to have a streamlined flow, should it have high density, high viscosity, or low density, low viscosity? What? So for streamlined flow, Reynolds number must be small. That means numerator must be small, means density must be less, and denominator must be big, so high viscosity. So low density and high viscosity liquids have a better streamlined flow. Is this clear, everyone? Any doubts on this? So how does this thing look like? Or this one. So here, what they're doing, right? They have a pipe of water and they're sending some ink from the left-hand side. You can control the speed of the water. If you increase the speed of the water, Reynolds number will increase, so flow becomes turbulent. So a slow-flowing liquid will be streamlined. A fast-moving liquid will be turbulent. So by controlling the speeds, you can make the flow turbulent or streamlined flow. You will see.
So we're saying that
the white
glass
at
right
the
there.
top
Okay. It's literally mixed.
is in there right now. It's just blue. It's completely unbroken.
Yes, and you can kind of tell by how clear the water looks.
And if you look at the very top, that looks like a complete tube. With
There are
no
actually
motion
2 streamlines
on top
inside.
of that flow on the bottom as well. When it's turbulent, you'll see like a white speck or reflection kind of speckling. And
What's the height order? Okay.
Dekh rahe streamline? There are 2 streamlines actually. Upper one is still hazy, but the bottom one, can you see it's such a sharp, fine line? And look at the remaining water, okay? It's pretty crystal clear, isn't it? Because the ink is not spreading. This is what I was saying. Once you send the ink, it will just follow that path. It won't spread out. But if you increase the flow now, it becomes turbulent.
with the strobe, it shows it too a little bit.
Can you see how it became bluish? The whole ink got spread out everywhere. The flow has become turbulent. Is this making sense, everyone? This is what I mean by streamline and turbulent flow. If I show you one more like that, this is how they actually send the ink. Can you see the machine on the left hand side? So they have a small nozzle and they're pumping ink from that, and you can see that line passing through that.
Like the pump's not on, is it? Slowly, yeah, very slowly.
So initially liquid is
Just
going slowly. You
yeah,
can see
very
the streamline. But if you increase the speed, you can see it gets messed up.
See how we're starting to get little. Yeah, keep it on one spot. All right. Okay. Now keep it there.
There.
Okay. I'll keep it.
So basically, this is a transition, streamline to turbulent.
Now turn. Feet are starting to.
And the flow has become completely turbulent. You can see how it is spreading off. So there, so you can mess up the Reynolds number by increasing the speed of the flow also. I hope now everyone got an idea, right? How streamlines look like. Is that clear, everyone? Great. So now we will limit our study to very special case. We study only ideal fluids. We will study streamline flow. In ideal fluids. So what do you mean by ideal fluids? First of all, there should be no viscosity. There should be incompressible, so density is constant. You don't want to study a liquid whose density is changing. Third, the liquid should be irrotational. Ever seen a liquid flowing? Sometimes they form whirlpools. We don't want to study such things. If there's a whirlpool, the flow gets messed up. We can't handle them. Meaning like this. This is a rotational flow. So you don't want water come beach mein. I don't want any whirlpools like this in the middle. We can't study them. So under these three assumptions we study. So we're studying streamline flow without viscosity, incompressible, and irrotational. Clear, everyone? Next thing. So how do you find the equation of the streamlines? So we kept on saying streamline, but if you want to find the equation, now look at the definition. We defined a streamline is where, the velocity vector is tangential. So if this is velocity v, if this is vx, this is theta, this is vy, the slope of the tangent tan theta is nothing but vy by vx, where tan theta is nothing but dy by dx. So then we have to integrate this and get it. So let me show an example how it looks. Example, let's say someone gives you velocity vy is 1 by xi cap minus 1 by yj cap. So this guy is your vx and this guy is your vy. So the slope dy by dx is vy by vx. We get dy by dx is equal to minus y by x. dy by y is equal to minus dx by x. Integrate on both sides. Yeah, I think I wrote reverse. This is y dy minus x dx. this is y square by 2 is equal to minus x square by 2 plus some constant. It's an indefinite integration. So we get an equation here. X square plus y square is equal to constant. What is this equation of? This is a circle, right? This is a circle. So for different values of constants, you get different circles. You know how will the streamline flow look like? Again, hypothetical thing, but here the streamlines are actually going in circles, concentric circles. The liquid is flowing like this. Can you tell me, is the liquid flowing clockwise or anti-clockwise? We know liquid is flowing in circles, concentric circles, but is it flowing clockwise or anti-clockwise? Look at here. If I put the x quadrant here, x comma y, Vx component is positive or negative? If x is positive, I cap is positive. So this is Vx. If y is positive, then Vy is negative. This is Vy. So velocity is flowing this way, na? So the liquid is actually flowing anti-clockwise, no, clockwise. Is this clear, everyone? You can try that in the third quadrant also. In third quadrant, x coordinate is negative, y coordinate is also negative. You will find I cap is negative, Vx is this way, and Vy is upward. Is that making sense? So that is how you can decide whether the liquid is flowing clockwise or anti-clockwise. Is this clear, everyone? This is how you can find the equation of the streamlines. Clear? We'll have a short break. Come back by 7:06. Any doubt so far? Chalo, come back in 8 minutes then. Chalo, let's start off. So that's how you find the equation of a streamline. So I'll give you one more equation. Now you guys try. So let's say velocity v is given by a plus bx I cap minus by j cap. So v is the velocity of the particles. A and b are constants. So find the equation of the streamlines and draw the streamlines. How will they look like? Try. I'll give you 2 minutes. So this is another variety of question they can ask you. Find the equation of the streamlines. Anyway, huh? Not sure what it did. What is the equation there? Slope dy by dx is vy, which is minus by vx is a plus bx. So this guy is dy by y minus dx b times by a plus bx. So once you wrote here, actually physics got over here, isn't it? Once you write that, physics got over. Now it is just max only. Now solve. I'll give you a minute. Now you have to integrate this. 1 by v. ऐसा ही कुछ आएगा अंश. But it's an indefinite integration, na? So constant आएगा. You're not putting limits. So you should say this plus this, you'll get plus constant. What is this integration here? Ln y. This is b by b ln a plus bx. So 1 by a plus bx integration is 1 by b, a plus bx plus some constant. So this guy would be ln y plus ln a plus bx is equal to constant. So you'll get y into a plus bx is some constant c. There. So y is equal to c by a plus b. If you see, actually this is a type of a hyperbola. X into y is constant. It looks like that. Now this c ka value can be anything. That has to be given. So for different values of c, you get different streamlines. Now, let's try to plot this. How does this function look like? Remember, all these are indefinite integration. There are no limits. So the equation is y is equal to c by a plus bx. When you put x is equal to 0, you get y coordinate is c by a. At x tending to infinity, y will tend to 0. Make sense? So as the streamline goes to x-axis, it tends towards x-axis. So the diagram would look like this. So if you take the constant c positive, let's say this is c1, so the streamline looks like this. If you take c2, the streamline looks like this. If you take c3, the streamline looks, so they're getting closer and closer to x-axis, but they'll never touch. You're getting, the liquid is getting closer to this. So this is for c positive. C3 is greater than C2 is greater than C1. Similarly, if you take minus C1, it looks like this. Minus C2 minus C3. There is one streamline on the center also. It is flowing along the x-axis. This is how the streamlines look. They start from the y-axis and they converge at the x-axis at infinity. The streamlines are getting closer and closer and closer, but they'll never meet. This is for C negative. Is this clear, everyone? So this is how the options will be. There'll be 4 graphs, and the last which of the following is the streamline flow. Like I said, the whole question is max. Any doubts on this integration? Clear, na? Ahna? Arush, Soham, Ojas, clear? Parth, Vignajit, Devika, Sharman, Devansh, clear? So that is a bit about streamlines. Next thing, equation of continuity. So this is another form of law of conservation of mass. X can't be negative. X can't be negative. हो सकता है. If you make X negative diagram कैसा दिखेगा? You can draw. I just draw to the right side. So X negative कैसे draw करोगे? If X is minus infinity, even then Y is 0. I'm not sure how this looks. For example, let's say X is negative and C is also negative. So will this be like this? So I don't know. I think that is how they would look. No? If X is negative, so it's like Y is equal to C by A minus BX. So as X ka value is increasing more and more, Y becomes negative. How does that look? So for a positive constant, so if you take C1 here, at some point Y will tend to infinity also. You'll get discontinuity here, left hand side. When if X is negative, there is a chance of this becoming 0, right? So then the value at a particular X, na? So if you take C1 here, this function is actually blowing off to infinity like this. And then again, the discontinuity function will come from here. That can't happen in real life. So you won't take the left-hand side graphs. It becomes a discontinuous function. Streamlines can't be discontinuous. Okay? So try to plot the graph and try to see if you can get something good. So this is based on law of conservation of mass. Yeah, if it has a point, it will be 2 tangents. So that also won't work. So we'll only take to the right-hand side for X greater than 0. I should have mentioned it. Like I said, it's a hypothetical thing. I just gave some equations. So let's say we have a part of a pipe here, and if you have a cross section A1, this is dx1, this is dx2, and this is A2. This is going with V2, and this is going with V1. So what equation of continuity says is the mass entering per second is equal to the mass leaving per second. There, that is the equation of continuity. Whatever mass enters must leave. So mass entering is rho A1 dx1. We can take even this thing by dt is equal to rho A2 dx2 by dt. Rho 1 is equal to rho 2 because it is incompressible liquid. We get A1 V1 is equal to A2 V2. This is nothing but volume flow per second. So area into velocity tells you how much liquid is flowing through the pipe. Example, let's say we have a pipe here. Let's say velocity is 3 centimeter per second. Area of cross section is 2 centimeters square. So the amount of liquid flowing out of this pipe is A into V is 6 centimeter cube per second. So every second this much liquid is coming out. Now the vector form of writing this flow let's say if this is your area vector and if this is your velocity vector and this is theta. So volume per second is AV cos theta, which is A bar dot V bar. So that's the vector form. But what do you mean by this exactly? Now liquid doesn't flow like that in a pipe, but if you take it rainwater, let's say rain is falling like this. So this is rain. This is that area vector A bar. So if the water is coming at an angle and the area is at an angle, then the rainwater collected per second is AV cos theta, which is A bar dot V bar. Yeah, that's the vector form of writing the volume flow per second. Remember, volume per second is a scalar. Area is a vector, velocity is a vector. Have a look at this. Clear, everyone? So simple thing, liquid mass entering is equal to mass leaving. That is a CET equation. Equation of continuity is another form of what? Law of conservation of momentum, law of conservation of mass, law of conservation of energy, law of conservation of angular momentum. They do ask such dumb questions. But you get it. But there are 150 questions. 50 max, 50 physics, 50 chemistry. And max, each question is 2 marks. So that's 100 for max, 50 for physics, and 50 for chem. Paper looks easy, but then again, if you want to get into VJTI computer science, you need to score at least 190 out of 200. Cutoffs are high. Next thing. Now, if I take one more example. So let's say liquid is flowing like this. So let's say this is A1, this is V1, this is A2, this is V2, this is A3, this is V3, and this is A4, and this is V4. Now again, what is the equation of continuity? A1, V1 is equal to A2, V2 is not equation of continuity. Liquid entering is equal to liquid leaving. That is the equation of continuity. So here, what is the liquid entering? A1, V1 is entering, A3, V3 is entering. That must be equal to the entire thing which is leaving A2, V2, and A4, V4. Clear with this? So not only for a single pipe, you can do this for multiple branches also. Is that clear, everyone? So let's say if you have a piston here, we have this injection. You must have seen it when you go to the doctor. This area is, let's say, A by 100, and let's say this area is 100, and this is liquid here. And if someone is pushing this piston by 1 centimeter per second, this is velocity v here. So A1 v1 is A2 v2. So this is A into 1, and that is A by 100 into v2. So we get v2 is 100 centimeter per second or 1 meter per second. This is what actually happens with your water cut tap. When you close your water tap with your finger, when you make the area half, the speed becomes double. Clear, everyone? The same way, when you open your water tap, did you observe initially the water ka thickness is more, as it goes down, thickness becomes small. Because as you go down, speed increases, so area of cross section decreases. So this is the reason when you open the water ka tap, you see the water ka jet, right? It becomes thinner like this, the stream. Clear? Let's see a question. We have a building height 20 meters. We have a water jet. Area A, speed is 10 meter per second. This angle is 60 degrees. So when you spray this water jet, it comes and falls somewhere on the ground. So water jet ka area won't remain same. So if you look at this FBD here, so when this water jet comes and hits the floor like this, there, this is the area where the water jet hits the floor. Let's call it A dash. So the questions, first one, how does the area of cross section change? Options will be area of cross section will always increase, always decrease, increase and decrease, decrease and increase. ऐसा 4 options होगा. What happens to area of cross section of the water jet? Initially it is A. Find the maximum area of the cross section of water jet. So during this entire motion, what is the maximum area of cross section? The third thing, find A dash. So when it hits the floor, it hits the floor of an area A, that horizontal thing, that thing which I showed you. How much is that area? Let's get this. It will increase and then decrease. Get the A dash, that's the actual one. Remember, A into V is constant. So the speed increases, area decreases, speed decreases, area increases. Let's see. So as the water jet goes up, what happens to the speed? It decreases, right? Till h max, the speed will decrease and the speed will increase. So if you actually look at the cross section, it increases and becomes maximum at h max and then decreases again. I'm exaggerating it. Speed decreases till h max and then it increases. Therefore, first area increases to max at h max and then decreases. Here the velocity is v. Here the velocity is v cos 60. The speed has become half. So this area of cross section is double. Is that clear, everyone? Then what about here then? Let the speed be some v dash. How to find v dash? This is 20 meters. Conservation of energy, everyone. So this is state 1 and this is state 2. So initial velocity half m 10 square plus mgh is equal to half m v dash square. So v dash will be 10 root 5. You can use conservation of energy directly. There's no need to use any kinematics and everything. So the area here will be a into v is equal to a dash into v dash. We get a dash is equal to a by root 5. But this is not the answer. There's a catch. See, when the water jet hits the floor, the water jet is hitting like this. So ask yourself, when this guy goes and hits the floor, it is spreading over a bigger area, na? Remember this thing? We did that question, water jet hitting at an angle. So water jet hits the floor not at a dash. So here what you got now, this area was a dash. Agreed? What I asked you is something else. So, okay, that I called a dash, yeah? So let me call this as a naught. So how do you find that? So this area, so this angle will be alpha. This is 90. This is 90 minus alpha. This is alpha. So this guy will be a dash by sine alpha. That's your answer, isn't it? But how do you find alpha now? How do you find alpha? In projectile motion, is there any relation between alpha and velocity? There is. Horizontal velocity is constant. U cos theta is equal to V dash cos alpha. Can you see how much you're using work power energy, fluid mechanics, this thing, everything. So horizontal velocity is constant. So this guy would be 10, V dash would be 10 root 5, and this is cos alpha. This is 10 by 2. So cos alpha is 1 by 2 root 5. So take this and substitute here, you'll get a naught from here. I'll leave the working to you. Numbers are not great. Are you getting the catch? So the main thing is that when you're hitting the floor, the area is a dash, but that is not the area on the floor. This thing will spread over the thing into bigger area. All clear with this? Abhinav, got this? Adi? Clear? Vihan, Poroja? Clear? Sharman? Arush? Arya? Nikhil? Next one. Let's see one more. this is a top view. Let's say you made a Z-shaped pipe. The pipe became thin like this. So this area is A by 2. This area is A by 2. This area is A, and this area is A. This is a top view. It's on a smooth floor. Let the pressure be P naught here. Let the pressure also be P naught here, which is not actually true, but for our case, let's take it as P naught. Let's say liquid is entering here with speed V. So the liquid enters here, goes through this, and comes out from this. So in this process, this entire pipe will have some force. So there is a tendency of this thing for the pipe to rotate. So exam options will be like this. So a liquid is flowing in a Z-shaped pipe as shown. Find the direction of the force and the torque on the pipe. So options will be like this. The pipe will move towards the right, rotate clockwise. Pipe will move to the left, rotate anti-clockwise. Pipe will move northeast. Pipe will move northwest, southeast, southwest, clockwise, anti-clockwise. These are 4 options they'll make. So what is the tendency of this pipe to move and rotate? Meaning if there is no one to stop you from moving, is a smooth floor, let's say, which way this pipe would move and which way the pipe would rotate. Find direction of force and torque on the pipe. Okay. I'm just asking for torque direction record. Who is asking you to calculate? Southeast. नेरे अंश साउथ नहीं है. Southwest. Look at this. First of all, the liquid ka speed here, if this is V, here it is V, here the speed becomes 2V, and here it comes out with 2V. And we know the force due to a water jet is rho A V square. So look at this thing. So this liquid here is going straight and hitting this. So this will exert a force of rho A V square. The liquid is leaving here. So by Newton's third law, it will exert a force in the opposite direction. Are you getting it? If you catch a water pipe, the water will go front and it will push you backward, right? The same way, this water will come and hit here. Now remember, the area has become rho, area became half, but the speed became double. So this is actually 2 rho AV square. Water is leaving, so this will be 2 rho AV square. So if you look at the net force, so this guy will be rho AV square root 2. This guy will be 2 root 2 rho AV square. Meaning if you actually try to calculate the force also, this guy would be, you can see this guy is dominating more than this guy. So force is rho A V square minus I cap minus J cap. So that is southwest. And torque is which way? This is rotating this way, this is rotating this way, clockwise. This is the reason when you're building water pipelines for a city, the big pipelines, you don't make sharp turns like this. The pipes will burst at this cross sections. It has to be a very gentle curve. Clear? Mostly a theoretical one. Next one. Any doubts on this? If the areas had been equal, then the force would have been 0, right? If areas are equal, the force would have been 0. It would be only a couple. There'll be only rotation and there'll be no translation. The next one is Bernoulli equation. If we point the hose 90 degrees upward, will it area become infinity? Why it will become infinity? It will just stop.
And so velocity becomes 0.
So, but the pressure also will change, right? Why will it remain in a pipe anymore? God. You'll start getting a fountain kind of thing. Which previous thing you're talking about? This is a top view, right? This is on a floor.
No, sir, before that, the kinematics.
Okay.
So if you point it upwards, what would be the area?
You tell me. You don't know what happens if you put a water jet upward. You must not have seen enough cartoons. It will become like this, right? It will try to spread this way. But because of gravity, it falls down. So if V is 0, what will happen? It will just try to spread in an infinite plane, isn't it? Think of like, let's say there is your floor में there is a water leakage. कभी देखा road में drainage leakage कैसा होता है? The water just spreads everywhere, isn't it? Isn't that a way of saying the area is tending to infinity? Kind of. Next thing, Bernoulli's equation. So this is valid for a streamline. This is based on law of conservation of energy. So let's see what is this. The derivation is important for HSE part, but result is more important for us. But let's see anyways. So this is an FBD of a part of a pipe. So we have a pipe there. We are taking a small cross section of it. Let this height be H2. Let this height be H1. Take a small cross section here. Area A1, pressure P1, velocity V1, width is dx1. dx2, A2, pressure P2, velocity V2. So like I said, 3 variables we are studying: pressure, height, and velocity. So first thing comes from the equation of continuity. A1 V1 is equal to A2 V2, which is A1 dx1 by dt is A2 dx2. So the amount of liquid entering is equal to the liquid leaving. Next thing, if you just look at this pipe here, so here the force acting is pressure P1 into A1. The displacement is dx1. On this thing, the pressure is pushing this way opposite P2 A2 and the displacement is dx2. So work done by the pressure. So the pressure on both the sides is pushing the liquid. So the left hand one is pushing P1 A1 dx1, force into displacement. This is P2 A2 minus sin dx2 because the force is opposite to the displacement. What is change in potential energy for this small liquid? mgh2 minus mgh1. What is mass? Density, area, thickness. So this is mass mgh2 minus density, area, thickness. This is the initial mass, which is g into h1. Is that making sense, everyone? mgh2 minus mgh1. Mass is nothing but density into volume, and volume is area into thickness. Change in kinetic energy is half m rho a2 dx2 v2 square, half m v2 square, minus half m, that is rho a1 dx1 v1 square. So when the liquid goes from point 1 to point 2, there's a change in potential energy, there's a change in kinetic energy, and there's a work done by pressure. Now using work energy theorem, what is work done by external force? Change in potential energy plus change in kinetic energy. Any doubts on this page, please ask me. So now using work energy theorem, work done by external force is change in potential energy plus change in kinetic energy. This guy will be P1 A1 dx1, P2 A2 dx2. This would be rho A1 dx1 G H2 minus rho A1 dx1 G H1 plus half mv2 square minus v1 square. But I know a1 dx1 is equal to a2 dx2. So this guy, this goes off. So you end up with P1 minus P2 is equal to rho G H2 minus rho G H1 plus half rho V2 square minus half rho V1 square. Rearrange the terms, you will end up with P1 plus rho G H1. So what we did here, we took two random points and we proved the pressure at that point, rho G H at that point, and half rho V square at this point, the sum is always constant. So that means you take any point on the streamline, you can say the pressure, the rho G H, the height, plus half rho V square, the sum of these three terms remains constant. There. This is the final form of the Bernoulli's equation there. Now, if you actually try to understand each term, let's see what it means. This thing is pressure, but if you actually multiply with volume, it is pressure into volume is work done. We saw in thermodynamics. This is work done by pressure per unit volume. So there's a technical name for this. This is called as pressure head. That is important for units and dimensions. They'll ask you what are the dimensions of pressure head. This is nothing but potential energy per unit volume. See, if you multiply rho into volume, you'll get mass. mgh is potential energy. This is called as potential energy head. This is nothing but kinetic energy per unit volume. If you multiply it with volume, it will become kinetic energy. This is called kinetic energy head. So in this, P is the pressure, H is the height from the reference, and V is the velocity. Have a look at this. Clear, everyone? Now this Bernoulli equation, right? If you see, again, theoretical thing, if they ask you when is this applicable between which 2 points, Bernoulli's equation is valid for 2 points on a streamline. You can't actually apply anywhere to anywhere. Bernoulli's equation is valid for 2 points on a streamline. So if you take streamlines like this, if you consider, let's say this is 0.1, this is 0.2, this is 0.3, this is 0.4, this is 0.5, and this is 0.6. So you can apply Bernoulli only for 2 and 3 because they're on the same line. You can't apply between 1 and 3, 1 and 5, or 1 and 6. But then what we say, by symmetry, all these lines look identical. Therefore, 3 and 5 are same. We use that symmetry argument and then we say it is okay. But theoretically speaking, it is only valid for 0.2 and 3. You cannot apply Bernoulli directly between 1 and 5. So what we do is this. By symmetry, 1 and 2 are identical. By symmetry, 3 and 5 are identical. 2 and 3 it is applicable. Therefore, 1 and 5 we can apply. We say something of that sort and we use it. Clear? But theoretically speaking, you can apply Bernoulli on one streamline. The next one, this is important. This is a modified Bernoulli. Now for gases, we have a problem. Unlike liquids, right? Gases, whenever there's a change in pressure or change in volume, temperature changes. So Bernoulli's equation, right? When you apply for fluids, generally temperature doesn't change, so we don't have a problem. But for gases, it becomes an issue actually. For gases, the temperature changes during the flow. If the gas suddenly goes from big area to small area or small area to big area, it is an adiabatic compression, isn't it? So if the gas suddenly goes from, let's say, small area and opens to a big one, it will suddenly expand. So there is a cooling. The gas ka temperature starts messing up. So the temperature changes during the flow. So we have to include the internal energy of the gas. Because we said it is a end of the day, it's an energy law of conservation of energy. So we have to include the internal energy. We'll not do the derivation. Internal energy has to be included. In case of liquids, temperature remains constant, so we can ignore it. So your equation becomes like this: pressure plus rho GH. This is potential energy ka term. This is kinetic energy ka term. Remember, work per unit volume, potential energy per unit volume, kinetic energy per unit volume, internal energy per unit volume. So there will be 4 terms now. We will see a question on this later on. Yeah, but most is an advanced one. Means they won't touch this. This is internal energy per unit volume. I hope you remember what is internal energy. याद है? du is F by 2 nr dt. Okay, DG. Internal energy per unit volume. This is your modified Bernoulli. So if you're using for gases, use this equation. You can't use that again, assuming temperature is constant, then this term becomes 0 du term. Temperature changes, we have to use that. Clear, everyone? Any doubts on this? Clear na, Vihan? Ansh? Adi? Ishana? Ojas? Pratik? Arya? Parth? Soham? Arnav? Perfect. Now, if you actually try to find the force on a bent pipe in a flow, so in the previous problem when we did, we took pressure is same, but in reality pressure also changes. So force on a bent pipe in a horizontal plane. So if you have a pipe like this is A1, this is A2, this is V2, this is V1, this is P1, and this is P2. So if you actually draw the FBD, So the forces will be pressure into area, and the liquid is going. So force is rho A1 V1 square. This is P2 into area. So we ignored that pressure in that question which I gave you. But anyway, there I asked you only the force of direction of force and the torque. So rho A2 V2 square. So when we calculate this, this will be P1 A1 plus rho 1 A1 B1 square. This will be P2 A2 plus rho A2 V2 square. There we have to find the resultant of these two. If this is given as theta, so then you can measure this. Clear with this? And what is the relation between the pressures? P1 plus half rho V1 square. Rho GH is equal to P2 plus half rho V2 square. Rho GH. Height is same because you said same plane. That will be the relation between P1 and V2. So if they ask you a question like this, water is flowing in a pipe, and if you take a small part of the pipe, what is the force? You have to include the pressure. In this problem, what happened was everywhere the pressure was P0, so P0 is cancelling out from outside. We didn't care. But technically speaking, the pressure does get messed up. So this is the actual equation. Clear with this? You have to include the pressure due to the liquid inside the pipe also. Clear, everyone? So for theoretical thing, that is okay. But if you actually want to calculate, this is how you do. That is about the Bernoulli there. So in Bernoulli, right, we have four main things. One is velocity of efflux. That is the most important one out of all. The second one is a Magnus effect and Venturi meter and a siphon. So the last three are mostly theoretical. So next class, when we catch up, we'll continue from here. We will wrap up the chapter next class. And if time permits, we'll start off with viscosity introduction also. But let's see. I think velocity of efflux will take some time. That there's some pretty good questions on that. So we'll catch up on next Tuesday. Now next Tuesday we'll have class at 5:30 as usual. We will change back to 5:30. I think the other person ka classes are back to normal or something. So Tuesday we'll catch up at 5:30. So yeah, and this week a test is online. So till Friday. So make sure to give. Right, we are going to have a meeting in 1 or 2 weeks. I'll let you know the dates. Mostly in 2 weeks we'll have a small seminar also, meaning PTM. We'll be discussing why some of